Connect. Awesome. We're live. Welcome, everybody. Yep, we are. I think so. Good afternoon, everyone. So good to have everyone here and have such an amazing turnout, some diverse industries, some familiar faces, some new faces as well. It's really great to have you all here. And yeah, we're hoping that today we're going to show you something fantastically interesting, and hopefully you'll leave this webinar knowing a little bit about what we've been doing here at Foresight Simulation and where we're going with it. As everyone's aware, today's topic is Unlocking AI's Potential. I'm the presenter, Kinu Dunbar, and co-hosting with me is Jaco Botha, the Managing Director of Foresight Simulation. In today's webinar, we're going to be covering 6 different topics. We're going to have Jaco start us off with an introduction on why we're here and what we're doing. And then from there, I'm going to take you into a little bit of what artificial neural networks are and where they stand in AI. So a little bit of history, a little bit of education before we get everything started. And then from there, we're going to move into how do we use artificial neural networks in open pit operations, and what are their benefits and those kinds of things. And I'm going to touch briefly in topic 4 about what kind of data is required to realize artificial neural networks in simulation. And yeah, then as I said, quantifying some benefits. And finally, we'll open up the floor to a Q&A. We will be watching the comments section, so any comments that get highlighted along the way we'll discuss towards the end of the webinar. But yeah, without further ado, I'm going to hand you over to Jaco, and he'll take you through our first section.
Thank you, Kinu, and welcome from my side as well. This is our first webinar on this topic of mine truck dispatch optimization, and I think it's really relevant because we all know that load and haul makes up about 50% of the operating cost of most open pit mines. So the size of the prize is massive. We're talking tens of millions of rands per month of operating costs for a typical mining truck. Hence the sheer amount of research that we came across as it relates to optimizing truck dispatch. But I think it's a bit of a double-edged sword because there's so much material, it's almost confusing. So we've been doing a lot of work to try and make sense of it. And I think what hinders the industry a little bit is really the just the complexity and really the cost, subsequent cost because of all the research. So as Kinu said, we're going to see how we can actually use our own data and artificial neural networks in order to make better decisions. Okay, so why are we embarking on this? You know, from our experience, we've seen this is a really complex problem. And as I mentioned before, there's so many techniques. The most basic one really is FTA, or fixed truck assignment. So that is really just a calculation based on matching trucks and shovels. So it's a bit of a static approach. Nothing wrong with it. You know, it's better than a random type of dispatch, but it's quite rudimentary. What we see most in the industry is some kind of linear programming, and that's really looking at all the constraints in the mine, whether it's at the crusher or our tips, and even at the shovel itself. That's the other approach. And then we also come across all the mixed integer linear or non-linear programming. And that really is looking at a lot of, you know, your more non-linear relationships. And it's a bit more advanced than our linear programming approaches. What we see a lot is the multi-criteria optimization. So that is what I think most of the dispatch systems use. And it's got multiple goals. And the problem really, it's quite subjective around the user. Does he want to maximize the truck utilization? Does he want to maximize the shovel utilization? or actually look at minimizing queuing time. So there's so many of these objectives and can all have different weights, but we don't really know, is it the best answer, yes or no? So it's a lot of trial and error to get the best answers out of these types of optimizations. And what Kino will show you is how we can use the ANN to actually possibly eliminate the need for all these different types of very complex heuristics that we see in a lot of these, mostly in the mining softwares that's used at different mines.
Yeah, no, that's awesome. Yeah, as Jaco kind of pointed out, I think it's so important for us to understand where we're coming from, what we have in industry at the moment, and where we can move to, and what the drawbacks and benefits are of these different types of dispatch algorithms. And yeah, so right now what I'm going to go through is kind of what is artificial neural networks, where do they stand in AI. I think there's a bit of a discrepancy at the moment between AI as the buzzword in industry at the moment and ChatGPT and all of these large language models that we come across, and what AI is as an entire field. First of all, the term artificial intelligence, first instance I can see of it, it was coined in the year 1955. And as the Oxford Dictionary defines it, it's the theory and development of computer systems able to perform tasks normally requiring human intelligence, such as visual perception, speech recognition, decision-making, and translation between languages. So essentially, Google Translate is AI to an extent. It's a much broader field than I think a lot of people give it credit for. But within the sphere of AI is where we find machine learning. So it's a section of AI, it's not AI itself. And in machine learning, the name is kind of pretty straightforward, but a machine that can learn. What does that mean? It means it can take information, it can generate outcomes or predicted outcomes from that information, and you can then give it multiple examples, and if it's incorrect by any amount, it starts correcting itself and becoming more accurate over time. So it learns the system and the environments in which you place it. And finally, when we get into a section of machine learning called deep learning, this is where you have your large language models and those very complex neural networks that take megawatts of power to make them able to answer all of your questions online. So yeah, it's a bigger sphere than I think a lot of us give it credit. Within machine learning itself, though, now, so if it's AI, the second sphere is machine learning, and this is kind of where we're starting to dig towards what a artificial neural network is. There are three main categories. You have unsupervised learning, supervised learning, and reinforcement learning. The first category, or the one on the left, unsupervised learning, this is, they all differ. Each one of these three differ in the type of data that you give them and the environment in which you place them. So for the first one, unsupervised learning, imagine a data model where you just have information. You don't have any outcomes from that information. So it's just all your data. And what a unsupervised learning machine learning algorithm will do is it'll find patterns, it'll dig through that data and give you insights. So it learns patterns and groups things together in your data. But by direct contrast, a supervised learning algorithm will take all of that input data that you have, and there'll be outputs associated with it. So instead of just having data, you have data with outcomes. So in the case of a mining example, you would have a whole bunch of data about perhaps how many vehicles were in a queue at different excavators. And as a result, this is how long it took for the last vehicle to get to the front of the queue. So you have inputs, how many vehicles, you have outputs, the time it takes to get to the front of the queue. And yeah, so that's the key difference between unsupervised and supervised learning. The last type of learning is kind of, it's easiest to explain with an example. So a reinforcement learning model will learn an environment. It explores an environment and it understands the rules in that environment, and then it seeks out an objective. So, for example, with chess, how we have all of these chess AI bots, and what they did is they started off with an objective, checkmate the king, and they had to explore that environment. Every single permutation, every single possible move that could happen, they'd explored it and they remembered it. They have much better memory than us. But eventually that means that they can achieve their objective sometimes far more effectively than we can. But for today's case, we're going to be focusing on supervised learning. And within supervised learning, this is where we now finally reach into what is an artificial neural network. So an artificial neural network, I'm sure everyone by now has probably seen an image that looks something like this. This is kind of the best representation that we have at the moment to explain what a neural network looks like. It's obviously all done on the cloud or in a computer, so there's no actual representation of it, but this is possibly one of the best ways to visualize and intuitively understand a neural network. First of all, there's three main parts to it. There's inputs, that's the information that you're feeding it. There are hidden layers, and that's where a whole bunch of complex calculus mathematics happens. I'm not going to dive too much into that today. We're just going to cover kind of the surface level things. And then finally, those hidden layers will convert to your output layer. And that is the neural network's guess, the best estimation that it has for the information that you've given it. And within a neural network, you have kind of two main parts, and that's a neuron. Think of it as a placeholder, something that stores information. It'll be a number between 0 and 1. And I'll do a little example just now of how information flows through this network. But imagine a color for 0 would be a dark color, and a color for 1 would be a bright color, so a whitish color. And that kind of represents our data. So if I fed this neural network one input where, say, in this example, it's maybe 0.6, it will transfer information along the pathways, and these pathways are connecting neurons to each other. In each pathway, there is a weight and a bias that says how strong is the relationship between the first neuron and the next neuron in the subsequent layer. So that's kind of what you would see. The strengths would pass through into the next layer. And all of these neurons would then light up with their respective color, and they would transfer their information and their weights and biases to the subsequent layer of neural networks, of hidden neurons. And from there, again, transfer to the next layer, and eventually you get your final outputs. And this is kind of the prediction that the neural network is making. So if we're trying to maximize here, and a white color would be the best kind of option, then this neural network would have chosen that option. Okay, so hopefully that clears up what a neural network is, so that now we can finally move on to how is it that we're using it, and specifically in simulation, and we're going to try and keep to the truck dispatch aspect of it. So first of all, the most important thing is to have a benchmark model. This is the model that you're going to compare to the optimized model. So you're going to compare this benchmark to a neural network that optimizes fleet dispatch. And that's important for multiple reasons. First of all, you want to be representative of the environment that you're modeling. You want to make sure that this is what happens in the environment, and we're doing that justice. The second step, of course, is defining what do we want this neural network to do. Do we want it to optimize to minimize queuing time? Do we want it to improve our cycle time? Do we want it to improve overall throughput, excavator utilization, etc.? That kind of thing has to be defined before moving on to step 3. So the simulation software that we use, Simio, it has an integrated feature for neural networks, which is really handy. It means that a lot of the difficult coding and whatnot is done automatically. But what it also means is that instead of using data directly from the operation, it can generate its own data in the simulation itself. So instead of running from hundreds of thousands of records of data where some of that data hasn't been verified or validated and tested, the simulation can streamline the data capture process and ensure that the data that we're using is accurate and reliable according to the environment. And finally, once that data is generated, the artificial neural network will then be trained from that data that you've generated. And that's where all of the predictions and stuff will come. That's where that neural network learns to predict better and better over time. Step 5, hyperparameter tweaking. This is quite a difficult section. This is changing the underlying structure of the neural network, so your hidden layers. How many layers do you want? What kind of combination of neurons do you want? Do you want 20, 30, 40, 10, 5 neurons in each layer? And you can adjust all of those different things. And finally, once you've done all of that hyperparameter tweaking, you go on to verification, validation, and testing. So we're now testing to ensure, hey, does this neural network actually result in an improvement in our overall objective function? And finally, down the line, what we want to get to is integrating that model into some sort of operation that can then assist with dispatch in the field. And yeah, over time, step 8, you would see that the operational environment changes, new vehicles come in, old vehicles go out, new excavators, new paths, new blocks, etc. So it will have to be updated over time. And yeah, so that's model refinement. And then we can loop back to either step 6 or step 7, and we can continue to do that throughout the operation of the mine. So yeah, hopefully that breaks down a little bit of how we'd use it in simulation modeling. Now I can just, as I said, I was going to briefly touch on what are the data requirements for artificial neural networks in Simio. So ideally, most of the modeling that we do in a simulation environment is data-driven. We want to represent operations as they happen, and we want to have reliable data that drives behavior in the simulation. That's what enables us to test all these different outcomes and ensure that any questions that our clients have asked us, we can answer them, and we can answer them with confidence. Data-driven aspects, I've listed quite a few there, but yeah, travel durations, loading durations, dumping durations, maintenance, a big part of it, refueling as well. All of these different elements are used to drive model behavior, and that's what gives us a really good benchmark to then say, okay, we can now develop an artificial neural network model that optimizes dispatch from the data that we've been provided with. But in contrast, of course, some operations don't necessarily have all of the data that would be required. And in those cases, usually it's kind of a bit of a smaller operation, but in those cases, we can still simulate and get to a very accurate model. Just requires a little bit more client involvement, and also perhaps we go on site and we do a little bit of testing and we capture a little bit of data. But yeah, this is where, again, Simio's ability to generate training data for the model, for the algorithm in the simulation environment is actually really beneficial, because if there are gaps in data, or if there are instances of things that have never happened but could happen, the artificial neural network data generation package in Simio will enable us to generate data and fill those gaps in. And that enables us to model for just about every hypothetical scenario. The other benefit, and the final benefit for data generation, I wanted to touch briefly on there's two different types of errors or anomalies in data. There's anomalous data that's collected. So that's where something happened that never would happen. Say, for instance, a truck had a velocity of 70,000 k's an hour. That's never going to happen. But that is something that we have seen in data packages that we've received. So it is a possibility for something like that to happen. However, in contrast, there's anomalous behavior. So we're not just filtering out any data. There's still a possibility that a vehicle got stuck in a queue for a lot longer than it should have. There's still a couple of other possibilities for travel and congestion and all of these kinds of things. So we're not eliminating that data. We're not eliminating those possibilities. We're just eliminating the completely anomalous behavior, the anomalous data that has been collected. So the simulation overall is still very representative of the operation. And that just makes training the neural network a little bit easier and a little bit more streamlined as we progress into a final model. So finally, I think probably if there's a question, it would be, what are the potential benefits? Have we seen anything from these models that we've developed? And yeah, we have. We've got a couple of hypothetical models that we've developed. Don't worry, I'll go through this graph in a second. But a lot of effort has gone into determining how practical and how realistic is it to ensure that these neural networks do actually give us the answers that we want, do actually result in an improvement in dispatch when compared to other different types of dispatch techniques. So in this hypothetical experiment that we did, we had it was one static algorithm compared to 4 different dynamic dispatch algorithms, and also a random algorithm just to make sure that we're still performing better than if you just send vehicles anywhere, which all of them did. But yeah, in each one of these, so there's 5 algorithms in total. There's ANNSR, HRR, random static SR. I'll go through those in just a minute. But each one of those algorithms was given a scenario where they had 10, 20, 30, or 40 vehicles. And each one of those scenarios was run 10 times to say, okay, what is the variability and what is the average performance of this particular algorithm? So it makes for a very fair testing environment to make sure that, hey, this algorithm is actually performing better than the other algorithms tested. The ANSA algorithm, it's a nice term that I coined for it. It's an artificial neural network, but it's been confined by a specific ratio. And what that means is that we've taken this neural network from a single objective to a multi-objective criteria model. It's now saying, what is the best excavator that I can go to, given the position that I'm at now? So it's looking at every single route that it could go, and it's saying, okay, which is the best route? And then the specific ratio is making sure that we're not dispatching too many vehicles to one route. So even if there's an excavator whose performance is extremely far superior to another excavator, and what it's just making sure of is that this neural network doesn't dispatch every vehicle there, that we still have a fair utilization of vehicles and excavators throughout the pit. Obviously, I understand that this is quite a complex figure, so we're hoping to have in future another follow-up webinar that just kind of reports on how neural networks work against other dispatch algorithms. So we're going to compare it against some of these linear programs, and we want to compare it against other dynamic dispatch algorithms. So we'll keep you posted on anything involving that. But yeah, finally, what are the percentage results? What do we really see from all of these different models? And overall, what we've seen is using artificial neural networks, depending on the benchmark that you're comparing it to, we've seen 5 to 15% improvements in throughput, queuing reduction of 10 to 20%, and some cycle time decreases of 3 to 10%. That may sound like a really small amount of cycle time decrease, but if you're decreasing a cycle by 3% for every single trip and every single day, that will add up very quickly. But yeah, hopefully I've covered everything, and I'm going to just open the floor now. I think Jaco and I will hang around for a little bit and just hear what some of your questions are, and hopefully be able to answer them as best as we can. So yeah, please, if you have any questions, send them through.
Doesn't look like we're getting any questions, so I think you explained it really well, Kinu. Thanks a lot.
Let's hope so.
Yeah. I mean, just from my side to conclude, I think what people overlook is how things can change in a shift. Roads can deteriorate, shovels can go out of production, digging rates can change. So it's so dynamic, and that's really where we see a lot of potential for this. The other thing is people are not that great at prediction; they're more reactive, and this will actually, in the realm of Industry 4, really help you to make autonomous decisions.
Yeah.
All right.
No, I agree with what you're saying, Jaco. I think that's a good point. And, furthermore, once we have a benchmark model, it simplifies the modeling process. Moving over from many of these very, very complex algorithms, you allow this algorithm to make use of your data and the information that you have to learn from it. So instead of the manual development of deciding what your functions are, what your nonlinear or linear functions are, a lot of that process becomes automated. And I believe that that's incredibly beneficial overall for first of all, the development rate, but also for the simplicity and the understandability of the overall program that we're trying to develop here.
Yeah, that's correct. Okay, yeah, well, so feel free to reach out to us after this webinar. We'll be distributing it. It will be probably on LinkedIn, Niconet. For anyone who wants to watch that or schedule a session with us in the next few weeks, we're very happy to oblige. No questions, I'm quite surprised.